In the previous video, we used the concept of the rate determining step to determine the factors that can affect the rate for an E2 mechanism. And now in this video, we will see how to apply that material to problems that are typical of what you might see on exams. In this video, for comparison, we will also be working on problems that involve rates for SN2 and SN1 reactions. I already discussed those types of problems earlier in my previous series on SN2 and SN1 reactions. Now, we saw in the previous video that the type of alpha carbon, whether the alpha carbon is primary, secondary, or tertiary, is not a key factor for E2 mechanisms, and therefore in this video we will not include problems about types of alpha carbons. But you can still get some practice with problems about types of alpha carbons and how they can affect the rate for SN1 and SN2 by looking at those previous video series on SN2 and SN1 reactions. Please pause the video and try this problem. Now let's discuss. Did you notice that most of the parts of this problem can be answered based on our table? We can find O minus in this position, this column of our table, which tells us that O minus is a strong base. On the other hand, we can find S minus in the middle column of our table, which tells us that S minus is a weak base. So that allows us to say that this is a strong base, this is a weak base, and clearly then HO minus is a stronger base than HS minus. We still haven't finished the problem, we haven't justified our answer. The table doesn't tell you why O minus is a stronger base than S minus. So the new material we have to learn here is how to justify why O minus is a stronger base than S minus. You might want to pause the video and see if you can come up with a justification for that on your own. Well, we can find oxygen and sulfur in our periodic table, and we can see that they're both in the same column of the periodic table. I've discussed in my previous video series that when you're comparing elements from the same column of the periodic table, the key thing to focus on is usually the atomic size. The key difference to focus on here is that oxygen is a smaller atom and sulfur is a larger atom. Why would that make the oxygen into the stronger base? What you need to remind yourself is a base an electron donor or an electron receiver? I hope that was a really easy question for you. I hope it was easy for you to say that a base is an electron donor. A base is an electron donor. Now, the thing that makes these ions want to donate electrons is their negative formal charge. This wants to donate electrons because of its negative formal charge, and this wants to donate electrons because of its negative formal charge. But whichever has the more stable negative formal charge will be less eager to donate its electrons, and whichever has the less stable negative charge will be more eager to donate its electrons. Well, I think I've discussed in previous videos that nature prefers it when charges can be spread out over a larger area. A charge that's spread out over a larger area is more stable, and a charge that's concentrated in a smaller area is less stable. That's why the atomic size matters. A larger atom is better able to spread out and stabilize its the negative charge. And a smaller atom has less room to spread out and stabilize its negative charge. So here's the complete logic spelled out. The sulfur is the larger atom. Because it's the larger atom, it has more room to spread out its negative charge. And since the negative charge is more spread out on the sulfur, the negative charge is more stable on the sulfur. But if the negative charge is more stable, that means it's less eager to be donated. More stable means less reactive. To repeat, more stable means less reactive. So since the negative charge is more comfortable on the sulfur, it's less reactive, less eager to be donated, and that makes the sulfur a weaker base, because a base is something that wants to donate electrons. On the other hand, the oxygen is the smaller atom. Therefore, it has less room to spread out its negative charge. The negative charge is concentrated over a smaller area. That makes the negative charge less stable when it's on the oxygen. And a less stable negative charge is more reactive. Less stable means more reactive. To repeat, less stable means more reactive. When the negative formal charge is less stable, that means it's more reactive, more eager to be donated, which makes the oxygen the stronger base. So when you're comparing elements from the same column of the periodic table, base strength decreases as you move down a column. So actually I should draw on this arrow to show base strength is decreasing as we move down the column. Base strength would increase as we moved up a column. The reason for this is that as you move down a column, you encounter larger atoms which have more space to spread out and stabilize their negative charge, which makes them less reactive, less eager to donate their electrons. We can go ahead and complete our answer here. Now we know why the O- is the stronger base than the S-. So here's our justification. Sulfur is the larger atom, so its negative charge is more spread out, which makes its negative charge more stable, which makes it a weaker base. We could add even more detail and say that since the negative charge is more stable, it's less eager to be donated. And that's the reason why S- is a weaker base, because a base is an electron donor. So again, the pattern that we've learned is that when we're comparing base strength for elements from the same column of the periodic table, base strength decreases as you move down a column. Base strength increases as you move up a column. And the explanation for that is based on the atomic size. Elements that are further down in the table have more room to spread out their negative formal charge, making the negative charge more stable and less reactive. We have seen that when comparing base strength for different elements in the same column of the periodic table, the key factor to focus on is atomic size. A larger atom is a weaker base. Now, this rule is based on the atomic size of the specific atom that will be donating its electrons. This rule does not refer to the size of the entire basic molecule or ion as a whole. A larger atom is a weaker base, but you should not assume that a larger molecule will be a weaker base. Please pause the video and try this problem. Now let's go through the solution to this problem together. I'll start by numbering the carbons. I gave these two molecules the same numbers because they're the same molecule and because our whole purpose here is to compare these two reactions. Now, we're already given the formal charge. We do not need to use the table to figure out the mechanism because the mechanism is given in the problem. So we know that the mechanism here will be E2. So we can identify roles. Well, look at the formal charge. This negative formal charge indicates that the O- will act as our base. Remember that E2 uses a base, not a nucleophile. And here the sulfur has the negative charge, so we expect the sulfur to act as a base. Neutral bromine will be our leaving group, which means that carbon 1 will be our alpha carbon. Now, when we're comparing these reactions, we have to look for a difference between them. It's useless to compare the leaving groups in these two reactions because the reactions have the same leaving group. It's useless to compare the alpha carbons because they have the same alpha carbon. We have to compare the bases. We have to compare these two bases to decide which is the better base. Does base strength matter for an E2 reaction? Yes, we've learned that the quality of the base does matter for an E2 reaction. So which of these is the stronger base, O- or N-? Well, you will know the answer to that if you have this table memorized. Here's O-, in the right-hand column of the table, and here's S minus in the middle column of the table. So the table tells us that O minus is a strong base. O minus is a strong base, but the table tells us that S minus in the middle column is a weak base. This table tells us that S minus is a weak base. Well, since this first reaction has the stronger base, we expect this to be the faster reaction. Here's our answer. O minus is a stronger base than S minus, so reaction A will have a faster E2 reaction than reaction B. Remember again that the quality of the base does matter for the rate of an E2 reaction. Why? Because the base participates in the rate determining step for an E2 mechanism. How did we know that O minus was a stronger base than S minus? Well, one way you can know is if you have this table memorized. The table would tell you that O minus is a strong base and S minus a relatively weak base, and that would give you the information to choose between these bases. Let's make a few additional comments for this problem. First of all, remember it's not enough just to say that reaction A is faster. You have to justify your answer. We justified that by saying that the reason was that O minus was the stronger base than S minus. This might be a full credit answer, but some professors might possibly not consider this to be a full credit answer because we haven't explained why O minus is a stronger base than S minus. Some professors might want you to explain that. So here's a fuller version of the answer that fully justifies our answer. Now we've justified why we're saying that O minus is the stronger base. O minus is the stronger base because it's the smaller atom. The smaller atom has less space to spread out its negative charge, so the negative charge is less stable on the smaller atom, making the smaller atom more eager to donate electrons. Remember, a base is an electron donor, so we should base our justification on that. So we're using these ideas that we discussed previously in this video. When you're comparing two elements in the same column of the periodic table, like oxygen and sulfur, base strength decreases when you move down the column. Base strength increases when you move up the column, and that's based on atomic size. When you move down a column, you get to larger atoms with more room to spread out the negative charge, making the negative charge more stable and less eager to be donated. Remember, a base is an electron donor. So here's our fully justified answer. This is likely more detailed. This is likely to be more detailed than the professor would really require for full credit on this problem, but I gave some extra detail to fully justify how we know O minus is the stronger base than S minus. Remember that for this problem, we did not use the table to determine the mechanism to focus on. We focused on E2 for both reaction A and for reaction B because the problem told us to focus on E2. After all, did you notice that for reaction B, the table would actually have predicted that the major mechanism would be SN1. But we did not focus on SN1. Instead, for both reactions, we focused on E2 because that's what the problem told us to focus on. Please pause the video and try this problem. Now let's discuss. This is a problem that we can answer, most of the parts of this problem we can answer based on our table. We can find neutral oxygen in our table here. And we can see that according to the table, neutral oxygen is a poor nucleophile. And we can find neutral sulfur in the table here. And we can see based on the table that neutral sulfur is a good nucleophile. Now notice, focus on the formal charge. Here we're focusing on neutral oxygen and neutral sulfur. So make sure you find neutral oxygen and neutral sulfur in the table, not, say, negative oxygen. And notice that this problem is not focusing on base strength, it's focusing on nucleophile strength. So make sure you focus on nucleophile strength from the table. So now we can answer a lot of the problem. We know that the water is a poor nucleophile, and this compound with neutral sulfur is a good nucleophile. We know that water is the poor nucleophile. H2S is a good nucleophile, so clearly H2S is a better nucleophile than water. But we haven't quite finished answering this question. We haven't justified our answer. We haven't given an explanation for why this is the better and this is the worse nucleophile. Well, let's find oxygen and sulfur in the periodic table. Oxygen and sulfur are in the same column of the periodic table. So what we're asking is, as we move down a column of the periodic table, what happens to nucleophile ability? Well, here's the answer. This is the pattern for neutral nucleophiles. We're dealing here with neutral nucleophiles. The pattern for neutral nucleophiles is when you're comparing elements from the same column of the periodic table, nucleophile ability improves as you move down the column. So since the sulfur is further down in the column than the oxygen, the sulfur compound is the better nucleophile, and the oxygen compound is the worse nucleophile, following this pattern. Now, why? What's the justification? Why does nucleophile ability improve for neutral nucleophiles when we move down a column? Well, it's because when you move down a column, the atoms get larger. When you move down a column, the atoms get larger, and larger atoms are more polarizable. And more polarizable atoms are better nucleophiles. So sulfur is more polarizable than oxygen. That's the reason that it's a better nucleophile. As you move down a column in the periodic table, nucleophile ability improves for neutral nucleophiles because larger atoms are more polarizable. Now, that might not seem like a very adequate answer because I haven't explained what polarizability is, and I haven't explained why does polarizability affect nucleophile ability. I'm actually not going to get into those details because what I've said here would be enough justification for most professors for most exam problems to be considered a justified answer. So if you would like to learn more details about polarizability and why it affects nucleophile ability, you can find those details in your textbook. Let's make some additional comments. First, notice that this pattern is the pattern for neutral nucleophiles. This pattern does not apply to negative nucleophiles. The pattern for negative nucleophiles is more complicated and depends on the solvent. I'm not going to get into that in this video, but you can find information about comparing negative nucleophiles in your textbook. This is the pattern for comparing neutral nucleophiles from the same column of the periodic table. By the way, this pattern for bases works for both neutral and negative bases. This pattern for bases works for both neutral and negative bases. But this pattern for nucleophiles is specifically for neutral nucleophiles. Next comment, did you notice that the pattern for base strength seems like the opposite of the pattern for nucleophile strength? Base strength increases when you move up a column, whereas nucleophile ability for neutral nucleophiles increases when you move down a column. These have opposite trends. Is that what you would have expected, or is that surprising? Is it expected or surprising that the base trend is the opposite of the nucleophile trend? You might want to think about that. Well, I would say it's surprising that these have the opposite trend. It's surprising that when we're comparing elements in the same column, the trend for base strength is the opposite of the trend for nucleophile ability. This is surprising. Why is it surprising? Well, are bases electron donors or receivers? Are bases electron donors or receivers? You should know that bases are electron donors. And are nucleophiles electron donors or electron receivers? I hope it's easy for you to remember that nucleophiles are also electron donors. Bases are similar to nucleophiles because they're both electron donors. Well, since bases and nucleophiles are similar in the sense that they're both electron donors, we would probably have expected that they should have the same trend in the periodic table. Since they're both electron donors, the most natural prediction would be that the trend for base strength would be the same as the trend for nucleophile ability. So it is surprising. It is surprising that even though they're both electron donors, the trend for base strength is the opposite of the trend for nucleophile ability when you're comparing elements from the same column. That makes it especially important just to memorize these trends. It's especially important to memorize these trends since, especially the trend, I guess, for nucleophile ability, since we've given a less full justification for that. This trend for nucleophile ability is probably not what you would have predicted based on the trend for base strength, and therefore it's important to memorize it. We might have predicted that these would have the same trend, but it's simply an experimental fact. It's simply an experimental fact that, in fact, the trend for base strength is the opposite of the trend for nucleophile ability when we're comparing elements from the same column, and we just need to memorize that experimental fact. When we are comparing nucleophile ability for neutral nucleophiles with elements from the same column of the periodic table, the key factor to focus on is atomic size. The larger atom makes the better nucleophile. This rule is based on the atomic size of the specific atom in the nucleophile that will be donating its electrons. The rule does not refer to the size of the entire nucleophilic molecule as a whole. A larger atom makes a better nucleophile. But you should not assume that a larger molecule will be a better nucleophile. Please pause the video and try this problem. Now let's discuss. We can start by numbering. There are no ionic bonds or formal charges to detect, and we do not use the table to determine the mechanism because the problem told us the mechanism. We should consider SN2 mechanism for both of these reactions, regardless of what our table would predict. So we can assign some roles. We would prefer to use, so for an SN2 reaction, we're going to use a nucleophile, not a base. We'd prefer to use an atom with a negative formal charge as a nucleophile, but since there are no negative formal charges, we can use this neutral oxygen as the nucleophile because it has a lone pair. Also use this neutral sulfur as a nucleophile. It also has a lone pair. The neutral bromine will be our leaving group, which makes carbon 7 our alpha carbon. Now, we'd like to compare these two reactions, so we have to look for a way in which the reactions are different. The reactions have the same leaving group and the same alpha carbon, so that's not what we need to focus on. We need to focus on the nucleophiles, since the nucleophiles are different in these two cases. We want to know which of these has the better nucleophile. Because remember that we have seen that nucleophile quality does matter for the rate of an SN2 reaction. Well, we can use this table to tell us that a neutral oxygen is a poor nucleophile. But on the other hand, a neutral sulfur is a good nucleophile. So here we have a poor nucleophile, and here we have a good nucleophile. That tells us reaction B will be faster. Notice that it's very important to focus on the formal charges. A negative oxygen would be a good nucleophile, but in this case we have a neutral oxygen. That's a poor nucleophile. Notice that both of these compounds are all covalently bonded, all non-metal bonds, so there are no ionic bonds and no formal charges in those two compounds. Here's our answer. Neutral sulfur is a better nucleophile than neutral oxygen. So reaction B, using the neutral sulfur, will have a faster SN2 reaction than reaction A. Again, remember that nucleophile quality does matter for an SN2 reaction. Why? Because the nucleophile participates in the rate-determining step for SN2. Now, this might not be a full credit answer. We did explain why reaction B was faster, because it had a better nucleophile, but we didn't explain why neutral sulfur is a better nucleophile than neutral oxygen. So here's our more complete answer. Sulfur is the better nucleophile than oxygen because sulfur is more polarizable. As we discussed earlier, when you're comparing neutral nucleophiles from the same column of the periodic table, nucleophile ability improves as you move down the column because larger atoms are more polarizable. So we've used that idea to justify our answer here and explain why this sulfur molecule is a better nucleophile than the oxygen-containing molecule, because sulfur is more polarizable. So this level of detail would be sufficient, I think, for most professors. Most professors would consider this to be a full credit answer for most introductory organic chemistry courses. But if you would like to learn about what polarizability actually is and why it affects nucleophile ability, you can find that extra information in your textbook. Now, it's interesting to compare this SN2 problem that we just completed with the previous E2 problem that we completed just previously in this video. There's a lot of similarities here because they both use oxygen and sulfur compounds. But notice that the answer kind of reversed. For the SN2 problem, the sulfur compound gave the faster reaction. But for the E2 problem, the oxygen compound gave the faster reaction. And that's because SN2 uses a nucleophile, whereas E2 uses a base. Sulfur is a better nucleophile than oxygen, but sulfur is a worse base than oxygen. So it's important to see the differences between these two problems. Again, notice that neutral sulfur is a better nucleophile than neutral oxygen. But notice that sulfur is a worse base than oxygen. That accounts for the different answers in these two problems. As we've already previously discussed, when you're comparing elements from the same column of the periodic table, the trend for base strength is surprisingly the opposite of the trend for neutral nucleophiles. Base strength increases when we move up a column, but nucleophile ability for neutral nucleophiles increases when we move down a column. The bases and the nucleophiles have opposite trends. That's why we got somewhat opposite answers on this problem. Remember, we've said that that's kind of surprising. It's kind of surprising that the trend for base strength is the opposite of the trend for nucleophile ability, but that's an experimental fact that we need to have memorized, that it's an experimental fact that these have opposite trends, even if that's not what you might have expected. Again, when comparing elements from the same column of the periodic table, the trend for base strength is the opposite of the trend for nucleophile ability for neutral nucleophiles, and you need to have that memorized. That you can see why this sulfur compound is the better nucleophile than the oxygen compound, but the sulfur compound is the worse base than the oxygen compound. One of the most challenging aspects of your exam will be the need to keep switching gears back and forth between different mechanisms. Some problems will be about E2, some problems will be about SN2, some problems will be about SN1, some problems will be about other mechanisms like E1 or other mechanisms that you'll learn about. You have to keep changing gears and switching between different types of mechanisms, and the rules for each mechanism are different. So it's very easy to get confused when you have to keep switching gears. So this is a good example of the need to switch gears. We had to switch gears a little bit when we shifted from this E2 problem, where we focused on base strength, to this SN2 problem, where we focused on nucleophile ability. If you have this table memorized, that can help you. The table tells us that neutral sulfur is a better nucleophile than neutral oxygen, but the table also reminds us that O- is a stronger base than S-. Remember that the reason we considered an SN2 mechanism for reaction A was because the problem told us to. Our table would have not predicted SN2 for reaction A. Our table, I guess, would have predicted no reaction for reaction A, but the problem told us to consider SN2 for reaction A. Well, we would consider that SN2 would proceed very slowly for reaction A because it's using a poor nucleophile. Please pause the video and try this problem. Now let's discuss. We can number the carbons. There are no ionic bonds. There are no formal charges. We know what the mechanism is. We know the mechanism is SN1 because the problem told us to consider that mechanism. So we don't use the table to figure out the mechanism. The problem tells us the mechanism. For an SN1 mechanism, we look for a nucleophile. Well, we can use this neutral oxygen with its lone pair as a nucleophile and this neutral sulfur with its lone pair as a nucleophile. The neutral bromine will be our leaving group, which makes carbon 1 into our alpha carbon. Well, the difference between these two reactions is in the nucleophiles. We already discussed in the previous problem that neutral oxygen is in this column, which makes it a poor nucleophile. And neutral sulfur is in this column, which makes it a good nucleophile. So you might think that reaction B should be faster since it has a better nucleophile. But remember, this is an SN1 mechanism, and we've learned, strange as it might seem, nucleophile quality does not matter for an SN1 reaction. Nucleophile quality does not affect the rate of an SN1 reaction. So here's our answer. Neutral sulfur is a better nucleophile than neutral oxygen, but nevertheless, these two reactions will occur at the same rate for SN1, because nucleophile quality doesn't affect the rate for SN1. And we further justified our answer by mentioning that the reason that nucleophile quality doesn't affect the rate for SN1 is because for SN1, the nucleophile does not participate in the rate determining step. Here is the first rate determining step for an SN1 reaction, where the leaving group leaves to form the carbocation. The nucleophile doesn't participate in this first rate determining step, and that's the reason that nucleophile quality doesn't affect the rate for an SN1 reaction. I think this is a difficult problem because it would be, if you know that neutral sulfur is a better nucleophile than neutral oxygen, it would be natural to think that a better nucleophile would give you a faster reaction. But we've seen that it doesn't work that way with an SN1 mechanism. In our last three problems, we have reviewed that a better base makes an E2 reaction faster. A better nucleophile makes an SN2 reaction faster, but a better nucleophile does not increase the rate for an SN1 reaction. And the reason for that is that the base participates in the rate determining step for E2, and the nucleophile participates in the rate determining step for SN2, but the nucleophile does not participate in the rate determining step for SN1. So you can see that when you're doing problems like this, it's absolutely crucial to be clear about what mechanism you're using. These last three problems were quite similar, but they had different answers because they were using different mechanisms. When the problem was about E2, it was important to focus on base quality, not on nucleophile quality, because E2 uses a base, not a nucleophile. When the problem was focusing on SN2, it was important to focus on nucleophile quality, not base quality, because an SN2 uses a nucleophile, not a base. And when the problem was focusing on SN1, the SN1 uses a nucleophile, but we need to know that nucleophile quality doesn't affect the rate for an SN1 mechanism. When you're working on these types of problems, or really most any type of problem in OChem, it's crucial to clearly identify what mechanism you're thinking about, because different mechanisms behave in different ways. Please pause the video and try this problem. Now let's discuss. We could start by numbering. Notice that we should number the product consistent with our number for the starting materials. And I numbered both of these starting materials with the same numbers because they're the same molecule, and I want to compare the outcomes here. Now, in this case, the ionic bond and the formal charges have already been drawn in for us. This problem did not tell us the mechanisms, so we're going to have to figure out the mechanisms. We have a neutral chlorine here, which looks like a leaving group, which makes carbon 4 our alpha carbon. So in both cases, we will have a primary alpha carbon, and we expect to be using S- as our nucleophile or base because it has a negative formal charge, which makes it an electron donor. Now you can see that reaction A used the S- as a nucleophile. You can see that because the sulfur has joined the alpha carbon in the product, which shows that in reaction A, the sulfur acted like a nucleophile. And you can see that in reaction B, the sulfur acted like a base. You can see that because we got an alkene product. We know that if you start with a alkyl halide and use a base, you can do an elimination reaction to get an alkene product. So by looking at the products here, we can see that reaction A used S- as a nucleophile and reaction B used S- as a base. Using our table, we're in the top row of the table because we have a primary alpha carbon. And we're in the middle column of the table because we're using S- as our nucleophile or our base. So notice that the table predicts that the major mechanism here will be SN2. So that really gives us our answer right here. It looks like reaction A is an SN2 mechanism. It appears that reaction A occurred by an SN2 mechanism, and we know that that will be the fastest mechanism in these conditions. So it looks like reaction A will be faster than any other reaction in these conditions. What mechanism should we say reaction B occurred by? Well, if it's not occurring by SN2, in order to make an alkene, it would have to occur by E2 or E1. E1 also makes an alkene product. I guess it's better for concreteness to suppose that reaction B occurred by an E2 reaction. Obviously, E2 would be pretty slow in this situation, but it might occur at some very slow rate. That's probably better than considering that reaction B was an E1 reaction. We have a primary alpha carbon here, and just like SN1 reactions don't work for a primary alpha carbon, E1 reactions don't work for a primary alpha carbon either. So I suppose we should consider this to be an E2, a very slow E2. Now, remember, we have to justify our answer. And we can't really just say, well, reaction A is faster because of our table. That's probably not going to be considered a good answer. So a good way to justify our answer and to explain why SN2 is favored here over E2 is because from our table we know that S- is a good nucleophile. The table tells us that S- is a good nucleophile, and the table tells us that S- is a weak base. That's the reason why in these circumstances SN2 is favored over E2. Remember that base quality does matter for an E2 reaction. So an E2 reaction will be very slow with a weak base. Maybe not a rate of 0, but E2 will proceed very slowly with a weak base. And nucleophile quality matters for SN2. An SN2 reaction will proceed at a good rate when you have a good nucleophile. Here's our answer. We predict that reaction A will occur more quickly than reaction B. But remember, for credit, we need to justify our answer. So the key thing that you would want to mention to justify your answer is you would want to mention that reaction A is using a nucleophile while reaction B is using a base. And you would want to mention that S- is a good nucleophile, but a weak base. That's the justification for why the SN2 reaction is expected to proceed more quickly than the E2 reaction. Again, we know that base quality matters for an E2 reaction and nucleophile quality matters for an SN2 reaction because the base participates in the rate determining step for E2 and the nucleophile participates in the rate determining step for SN2. So one thing that's very helpful here is to understand clearly that E2 reactions use a base, whereas SN1 and SN2 reactions use a nucleophile. Again, you should have this table memorized. That's how we knew that S- was a good nucleophile and a weak base, because it was in this middle column for good nucleophiles and weak bases. Notice that this problem did not tell us what mechanism to consider. So how did we figure out the mechanism? Well, we partly figured out what mechanisms to consider by using the table, and we partly figured out what mechanisms to consider by looking at the products that were given to us. When they gave us this product, we could see that reaction A was a substitution reaction, not an elimination reaction. And when they gave us this product, we could see that reaction B was an elimination reaction, not a substitution reaction. Lastly, notice that S- is good at being a nucleophile and not that great at being a base. That's kind of surprising, isn't it? Isn't that kind of surprising? Because remember, both nucleophiles and bases are electron donors, right? A nucleophile is an electron donor and a base is an electron donor. So you might expect that if something is good at being a nucleophile, you might suspect that it's also going to be good at being a base. But you can see that that's not always true. Some things are good nucleophiles, but weak bases, the things in this middle column. Why is that? Well, I'm not going to go into those details in this video. I'm not going to explain why this is a good nucleophile and a weak base. I might discuss that later in another video series, or you might find a discussion of that in your textbook. But anyway, the point is, both nucleophiles and bases are electron donors. Nevertheless, you should not assume that a good nucleophile is automatically a strong base. Some good nucleophiles are strong bases, but some good nucleophiles are weak bases. When you tried this problem on your own, were you using the concepts of nucleophile and base? This is a good test of whether you've started using the ideas and concepts that we've been discussing in these videos. So I'm sure you've noticed that in these videos, I try to use the concepts of nucleophile, leaving group, acid, and base on every single problem. But I hope that you understand that the reason I'm doing that is because I'm hoping that you will do that as well. You need to start trying to use the concepts of nucleophile, electrophile, leaving group, acid, and base on every single OChem problem that you attack. So when you see me using those concepts, nucleophile, electrophile, leaving group, acid, and base, in the videos, remember that's supposed to be a model that you should be trying to imitate in your own work. On every problem that you work on, try to think in terms of nucleophile, electrophile, leaving group, acid, and base. I know that at first you might feel that that slows you down, but in the long term, that's the only way to really build any skill or understanding in organic chemistry. So again, this problem is a good test if you started building those skills. If you tried solving this problem without even thinking about the concepts of nucleophile and base, then you're not using those concepts enough. Remember, you should be thinking in terms of those roles in organic chemistry on pretty much every single OChem problem that you work on. You should be modeling that thought process on what I've been demonstrating in the videos, where in the videos on almost every problem, we go through the thought process by thinking in terms of the roles: nucleophile, electrophile, leaving group, acid, and base. The more you practice using and thinking about those roles, the more second nature they will become, and the more useful they'll become to you, and the more speed you'll be able to pick up. If we compare these four compounds, do you know how to figure out or how to rank the leaving groups from worst to best in these compounds? So let's learn how we can rank the leaving groups in these compounds. First, let's identify the leaving groups. Well, we've already learned that neutral chlorine, bromine, and iodine can be leaving groups. So let's compare that to the ability of fluorine to act as a leaving group. We want to rank all four of these leaving groups. Well, we should notice that these four leaving groups all appear in the same column of the periodic table. You can see that each of these four leaving groups, fluorine, chlorine, bromine, and iodine, appear in the same column of the periodic table. So what we're going to try to learn here is how to rank different leaving groups that appear in the same column of the periodic table. Do you know what the answer is? Do you know how to rank elements in the same column of the periodic table as leaving groups? Well, here's the answer. Leaving group ability generally improves as we move down the periodic table. Elements that are higher in the periodic table are generally worse leaving groups, and elements that are lower in the periodic table are generally better leaving groups. So we can use that right away to rank these compounds in terms of their leaving groups. In fact, we can see that these compounds are already arranged from worst to best leaving group. Fluorine is the highest in the periodic table, so fluorine would be the worst of these leaving groups. Chlorine is lower down, so that's a better leaving group. Bromine is below chlorine, so that's a better leaving group than chlorine. And iodide is the lowest of all of these in the periodic table, so iodide would be the best of these leaving groups. We can also categorize any leaving group as either a good leaving group or an unacceptable leaving group. So do you know how to class these? That's something we've already talked about in this video series. We've already seen previously that neutral chlorine, neutral bromine, and neutral iodide are considered good leaving groups, and neutral sulfonates are considered good leaving groups, and that other neutral atoms are usually not acceptable leaving groups. So based on those ideas, we would classify the neutral chlorine, neutral bromine, and neutral iodide as good leaving groups. And we would classify this fluorine as an unacceptable leaving group because it's not a neutral atom that we've learned on our list of good leaving groups. And of course, that's consistent with what we already expected. We expected fluorine to be the worst of these leaving groups because it's the highest in the periodic table. And in fact, that makes it an unacceptable leaving group. And we expected chlorine and bromine and iodide to be better leaving groups because they're lower in the periodic table. And in fact, all of those are considered to be good leaving groups. Chlorine, bromine, and iodide are all considered to be good leaving groups. But of course, when you're comparing them, bromine is a better leaving group than chlorine, and iodide is an even better leaving group than bromine. So of these good leaving groups, chlorine is the least good of the good leaving groups, and iodide is the best of those three good leaving groups. When we say that fluorine is an unacceptable leaving group, what we mean is that, for example, if we tried to do an E2 mechanism with a fluorine leaving group, the rate of the E2 mechanism would be close to zero. It might not be exactly zero, but an E2 mechanism with a fluorine leaving group would have a rate that's close to zero, a rate that's too small to be practical for most uses. On the other hand, when we say that chlorine, bromine, and iodide are good leaving groups, we mean, for example, that a E2 mechanism could occur at a substantial rate with any of those leaving groups. Nevertheless, since iodide is the best of those good leaving groups, E2, even though E2 could occur with chlorine, bromine, or iodide, the E2 would still be fastest with iodide, slower with bromine, slower with chlorine. And then, of course, E2 would be so slow with fluorine that the rate would be close to zero. Now that we've learned this trend for comparing leaving groups in the same column of the periodic table, naturally we should compare this to the trends for bases and nucleophiles that we learned about earlier in this video. So please pause the video and see if you can remember and write down what are the trends when you're comparing base strength and nucleophile ability for elements in the same column of the periodic table. Here's a summary of all of those trends. When comparing elements in the same column, leaving group ability improves when you move down a column. Base strength improves when you move up a column. And for neutral nucleophiles, nucleophile ability improves when you move down a column. Now, let's compare the trend for leaving group ability and the trend for base strength. I would say that the trend for leaving group ability is exactly what you would expect given the trend for base strength. These two trends are very consistent with each other. Now that might surprise you because it looks like the trends are pointing in opposite directions, but that's what you should have expected. You should have expected that the trend for leaving group ability would be the opposite to the trend for base strength, because leaving groups are kind of the opposite of bases. Do you see why I would say that? Well, remember that leaving groups are electron receivers, while bases are electron donors. You should know that a leaving group is an electron receiver, while a base is an electron donor. So in a sense, a leaving group is the opposite of a base. A leaving group is kind of the opposite of a base, because a leaving group receives electrons while a base donates electrons. Since these two roles are kind of opposite to each other, it makes good sense that their trends should be opposite. When we say that these small atoms are strong bases, we mean that these small atoms are good at donating electrons. These small atoms are good bases because they're good at donating electrons. Well, then it should make sense that the larger atoms will be good leaving groups because the larger atoms will be better at receiving electrons. If the smaller atoms are better at donating electrons, we would expect that the bigger atoms would be better at receiving electrons. So these two trends make good sense and are very consistent with each other. The trend for comparing leaving group ability when you're looking at elements in the same column is what you would expect given the trend for comparing base strength. The weird thing that's surprising that you would not expect just from thinking about it is the trend for nucleophile ability. This trend for nucleophile ability is not probably what you would predict based on the trends for leaving groups and bases. I already talked about that a little bit earlier in the video. Nucleophiles are electron donors. Nucleophiles are electron donors, which makes them similar to bases. Since both bases and nucleophiles are electron donors, you might have expected that they would have the same trend. But surprisingly, it turns out experimentally that the trend for nucleophiles, for neutral nucleophiles in the same column, is the opposite to the trend for bases, even though they're both electron donors. That's a surprising experimental fact that we just have to memorize. Similarly, leaving groups are kind of the opposite of nucleophiles. A leaving group is kind of the opposite of a nucleophile because leaving groups are electron receivers and nucleophiles are electron donors. But even though a leaving group is kind of the opposite of a nucleophile in terms of what they do with electrons, surprisingly, experimentally, it turns out that the trend for leaving group ability is the same as the trend for neutral nucleophile ability in the same column. That is a surprising trend, so it really just has to be memorized. So in summary, I think that the trends for leaving groups and for bases make good intuitive sense and are what you might have been able to figure out just by thinking about it. On the other hand, the trend for nucleophiles is surprising. It's probably not what you would have predicted just from thinking about it, and that means it's especially important to have this trend for nucleophiles memorized. So I was just saying that this trend for leaving groups makes pretty good sense, and you might have been able to figure it out just by thinking about it. It makes good sense that a larger atom should be a better leaving group, and that a smaller atom should be a worse leaving group. So the next thing I want to do is justify this trend. Now would be a good time to pause the video and see if you can figure this out for yourself. Can you figure out why a larger atom would be a better leaving group and a smaller atom would be a worse leaving group? Well, of course, you could just say that it makes good sense that this trend for leaving groups should be the opposite of the trend for bases. If bases' strength increases in this direction, it makes sense that leaving group ability should increase in this direction because leaving groups receive electrons while bases donate electrons. But let's try to explain that in more detail. Let's try to give a more detailed explanation for why a larger atom would be a better leaving group. Well, when judging leaving group ability, it turns out that it's usually best to focus on what the leaving group will look like after it leaves. So to start with here, can you pause the video and write down what these leaving groups would look like after they leave? Here's the answer to that. So here's what these leaving groups will look like after they leave. And the key thing is that after they leave, they will each have a negative formal charge. Remember, the most important factor to focus on in organic chemistry is formal charges. So what we need to focus on is which of these leaving groups will have the most stable negative charge after it leaves. Which of these will be best able to stabilize the negative charge? And the answer is the largest atom will be best able to stabilize the negative charge, because the largest atom has the most space to spread out the negative charge. The larger atom has more space to spread out the negative charge and stabilize the negative charge, and that means it will be easier for the larger atom to leave in the first place. That's the reason that larger atoms make better leaving groups. Here's a summary of that logic. The largest atom will have the most space to spread out the negative formal charge that it gains after leaving. Therefore, its negative charge will be the most stable, and that means it'll be the easiest for the largest atom to leave in the first place. On the other hand, the smallest atom, the fluorine, has the least space to spread out the negative charge after it leaves. That means that on the fluorine, the negative charge will be concentrated in a relatively small space, making the negative charge relatively unstable. Since the fluorine's negative charge will be relatively unstable after it leaves, that means it will be relatively difficult for the fluorine to leave in the first place, making the smallest atom the worst leaving group. I think we've talked about in the past that charges in general are most stable when they're spread out over a large area, and formal charges are least stable when they're concentrated in a small area. So now we've explained this trend in leaving groups. The largest atom will be the best leaving group because it has the most space to spread out and stabilize the negative formal charge after it leaves, making it the easiest meaning that it's the easiest for this atom to leave in the first place. Did you notice that our explanation of the trend for leaving groups was very similar and used very similar ideas to our explanation earlier in this video about the trend for base strength? Leaving group ability improves as we move down a column. Base strength improves as we move up a column. But those two explanations are consistent with each other. Those two phenomena are very consistent. It makes good sense that these trends move in opposite directions because a leaving group is an electron receiver while a base is an electron donor. Small atoms are strong bases because their negative charges are concentrated in a small area, making the negative charge relatively unstable and eager to be donated. A small atom is a strong base because its negative charge is concentrated and unstable and eager to be donated. And by the same token, a small atom makes a bad leaving group because after the leaving group leaves, its negative charge will be concentrated and unstable, and that makes it difficult for the leaving group to leave in the first place. The small size, atoms with small size, are eager to donate electrons, so it makes good sense that they're not that eager to receive electrons. And similarly, a large atom would be a weak base. A large atom would be a weak base because its negative charge would be spread out and stabilized and not very eager to be donated. And the same logic that makes a large atom not a good electron donor means that the large atom would be a good electron receiver. So the trend for leaving group ability is just what you would expect based on the trend for base strength. And in fact, they're both based on the same logic. They're both based on the logic that negative charges are more stable on large atoms where they can be more spread out, and negative charges are less stable on small atoms where they're more concentrated. In fact, if you look at your textbook's explanation for why large atoms are better leaving groups, many textbooks might just say that large atoms are better leaving groups because they're weaker bases. Many textbooks simply say that the weaker the base, the better the leaving group. To me, it seems clearer to say that large atoms are good leaving groups for the same reason that large atoms are weak bases. which is that large atoms have more space to spread out and stabilize their negative charge. On the other hand, remember that the trend for nucleophiles does not seem consistent with the trends for bases and for leaving groups. The trend for nucleophiles is surprising. After all, bases and nucleophiles are both electron donors, so the most natural expectation would be that they have the same trend. But surprisingly, even though bases and nucleophiles are both electron donors, they have opposite trends. Base strength increases when you move up a column, but for a neutral nucleophile, nucleophile ability increases when you move down the column. This is for neutral nucleophiles. So the trend for nucleophile ability is not based on the same logic that the trends for base strength and leaving group ability are based on. It's not, instead, nucleophile ability is based on this concept of polarizability, which, as I've mentioned, you could read about more in your textbook. Again, because this trend for nucleophile ability is surprising and seemingly not consistent with the other two trends, it's important simply to memorize this trend. In fact, you really should memorize all three of these trends. You should be careful to memorize all three of these trends for leaving group ability, base strength, and nucleophile ability. I think that we've been able to give a quite clear and reasonable explanation for the trends in leaving group ability and base strength. We didn't give an in-depth explanation for the trend in nucleophile ability. We just said that it's a surprising experimental fact that the trend works in this direction and that it's based on this concept of polarizability, which you could read about more in your textbook. Finally, let me remind you again that when judging leaving group ability, it's usually best to focus on what the leaving group will look like after it leaves. We saw how that was helpful when we were thinking about the trends for leaving group ability here. We have seen that when we're comparing leaving group ability for elements from the same column of the periodic table, the key factor to focus on is atomic size. A larger atom is a better leaving group. Now, some leaving groups consist of an actual group of more than one atom. But this rule is based on the atomic size of the specific atom in the group that will be gaining electrons. The rule does not refer to the size of the entire leaving group as a whole. A larger atom is a better leaving group, but you should not assume that a larger group of atoms will be a better leaving group. I will discuss this distinction between atomic size and the size of the entire leaving group a little bit later in this video. Please pause the video and try this problem. Now we can discuss. We can start by numbering, including this carbon. We can look for an ionic bond. Here's an ionic bond between oxygen and sodium, so we put in our formal charges. We expect the negative oxygen to act as a nucleophile or a base. We expect neutral bromine and neutral iodide to act as our leaving groups. So we expect carbon 1 to act as our alpha carbon. Now for choosing the mechanism, we should start by looking at the products that we were given. We can see from these products that the products are alkenes. So we can see that these will not be substitution mechanisms. Instead, they will be elimination mechanisms. Both E2 and E1 elimination mechanisms make alkenes. But to figure out whether this is E2 or E1, we need our table. We should notice that we have a secondary alpha carbon. Carbon 1 is secondary. With a secondary alpha carbon and O-, we're in the middle row and right-hand column. So our table predicts E2. So we should make a note that both reaction A and reaction B will be E2 mechanisms. And now we can update and say that we know that we're going to use the O- as our strong base, rather than as a nucleophile. Now we look for a way in which the reactions are different. It doesn't help to compare the bases because both bases are O-. It doesn't help to compare the alpha carbons because both alpha carbons are secondary. The difference that we need to compare is the leaving groups. We expect that the reaction with the better leaving group will be faster. because we know that leaving group ability does affect the rate for an E2 mechanism. The leaving group does participate in the rate determining step for an E2 mechanism, and therefore leaving group quality does matter for the rate of an E2 mechanism. Now we should recognize that both bromine and iodide, neutral bromine and neutral iodide, are both on our list of good leaving groups. But which is better? Here is bromine and here's iodide in the periodic table. They're both in the same column of the periodic table. And we've learned that when we're comparing leaving group ability for elements in the same column, leaving group ability improves as we move down the column. Since iodide is further down the column, we expect the iodide is the better leaving group and bromine is the worse leaving group. And that tells us that reaction B will have the faster rate. So we can begin our answer by saying that reaction B will be the faster E2 mechanism because iodide is a better leaving group than bromine. I think that many professors would consider this to be a full credit answer, but I think also there might be some professors who would want you to give a further justification and give further explanation for why the iodide is the better leaving group. So it might be safer to include some extra explanation. Iodide is the better leaving group we've seen because it's larger. And having a larger atomic size means the iodide is better able to spread out and stabilize its negative charge after it leaves, which makes it easier for the iodide to leave the alpha carbon in the first place. Now I've probably included a little more detail than the professor would probably require, but anyway, I tried to spell out in detail here what the logic is for why the iodide is the better leaving group. So what do you need to know in order to get this problem correct? Of course, you need to know that leaving group ability does matter for the rate of an E2 mechanism. And in fact, remember that leaving group quality matters for E2, leaving group quality matters for SN2, and leaving group quality also matters for SN1. If you use a better leaving group, that will improve the rate for E2 and for SN2 and for SN1, because the leaving group participates in the rate determining step for E2 and for SN2 and for SN1. But that won't do you any good unless you can figure out which is the better leaving group. So you need to know that when you're comparing elements in the same column of the periodic table, the larger atom will be the better leaving group. Well, this problem that we've just completed has tested the effect of leaving group ability on the rate of an E2 mechanism. Now, in the previous video, we saw that leaving group ability affects SN2 and SN1 reactions very similarly to how it affects E2 mechanisms. So I'm not including any additional problems in this document to specifically test the effect of leaving group ability on SN1 or SN2. But you can find problems that test the effect of leaving group ability on SN2 and SN1 in my previous video series on SN2 and SN1 reactions. Please pause the video and try this problem. I hope you actually tried this problem on paper. This is an important review of the material that we've been talking about. Here's the answer. Here's our answer. As you move down a column in the periodic table, leaving group ability improves. As you move down a column in the periodic table, base strength decreases. When moving down the column, base strength decreases. And for neutral nucleophiles, when we move down a column of the periodic table, nucleophile ability improves. These are the key ideas that you need to have, some of the key ideas you need to have memorized from this video. We've discussed that the trend for leaving group ability is just what you would expect based on the trend for base strength. These two trends are very consistent with each other, and we gave full explanations for the leaving group trend and the base trend based on the size of the atom. On the other hand, we said that the trend for nucleophiles is surprising and doesn't seem all that consistent with the trends for leaving groups and bases. So it's important to have memorized what the trend for nucleophiles is as an experimental fact. I encourage you to keep periodically reviewing these three trends. There's a good chance that you'll see a number of problems on your exam testing these trends, and it's easy to get these trends confused with each other unless you repeatedly review the trends. Notice that you have to talk in complete sentences here. It doesn't do any good to say larger atoms are better or smaller atoms are worse, because that may or may not be true based on the role that you're talking about. What you want to say is that a larger atom is a better leaving group, or a larger atom is a better nucleophile. But you'd want to say that a smaller atom is a stronger base. So it doesn't do any good just to say larger is better or smaller is worse. You have to always articulate what role you're thinking about, leaving group, base, or nucleophile. We have seen that for the trends we have discussed in this video, the key factor to focus on was the atomic size of the elements. So notice that we have not been focusing on the elements' electronegativities. But, of course, there are other situations in which you should focus on electronegativity. For example, when you're comparing different elements from the same row of the periodic table, in that situation, you usually should focus on the element's electronegativity. Now, in this video, I've focused on comparing leaving groups, bases, and nucleophiles with elements from the same column of the periodic table, simply because that tends to be more frequently tested than comparing leaving groups, bases, and nucleophiles with elements from the same row of the periodic table. But you should be able to find a discussion of how to use electronegativity to compare elements from the same row in your textbook. Now, for completeness, I should also mention that there are some situations, different from the ones discussed in this video, in which you should focus on electronegativity even when you're comparing elements in the same column. That occurs when you're considering how well an element can stabilize the negative charge on a nearby atom rather than on itself. But for the sake of simplicity, I'm not going to go into further detail about that type of situation in this video. I'll take this opportunity to remind you that when we're comparing these elements from the same column of the periodic table, all of these trends are based in one way or another on the size of the atom. Again, it's the size of the atom that matters, not the size of the whole group. Don't worry about the size of the entire leaving group or the entire base or the entire nucleophile. Just focus on the size of the individual atom that will be donating or receiving electrons. Which of these molecules has the better leaving group? Well, you should know that this molecule is an alkyl sulfonate, and therefore it contains a good leaving group. Whereas an ordinary neutral oxygen is not in our list of good leaving groups, so this would be an unacceptable leaving group. Now, why? Why is this sulfonate a good leaving group, whereas this neutral oxygen is a poor leaving group? Well, here's the wrong answer. After learning the previous material, sometimes students will tell me that the sulfonate is a better leaving group because it's bigger. This group looks bigger than this group, so some students wrongly tell me that this is a better leaving group because it's bigger. But remember, that's a wrong explanation. Because remember, only the size of the only atomic size of the leaving group atom affects leaving group ability. The size of the entire leaving group as a whole does not directly affect leaving group ability. The specific leaving group atom here is the oxygen. That's the one that's going to leave the alpha carbon, and the specific leaving group atom here is also an oxygen. The size of the leaving group atom that's going to actually gain the negative formal charge is the same for both of these pictures. In this case, this oxygen will gain the negative formal charge, and in this case, this oxygen will gain the negative formal charge, and those two oxygens have the same size. The size of the leaving group as a whole doesn't really matter. So you should not say that this sulfonate is a better leaving group because it's bigger than this alcohol group. That's not the correct explanation. Do you know what is the correct explanation? Why is a sulfonate group a better leaving group than an alcohol? Can you answer that question? This is actually a topic that I discussed in my SN2 reactions video series. Well, remember that to judge leaving group quality, we should probably think about what the leaving groups will look like after they leave. Here's what these two leaving groups would look like after they leave. After they leave, when judging leaving group ability, it's usually best to focus on what the leaving group will look like after it leaves. After they leave, these leaving groups will have gained a negative formal charge. So whichever group is better able to stabilize the negative charge after it leaves will find it easier to leave in the first place. Well, the sulfonate will have the more stable negative charge, but it's not because the group is larger. Remember that the size of the entire group is not what's relevant. The only sizes we would compare are the sizes of these two oxygens, the oxygens that bear the negative charge, and those are the same size. So it's not the size that makes the difference here. This leaving group is more stable after it leaves because its resonance stabilized. This negative charge is resonance stabilized, which makes it easier for this oxygen to leave in the first place. This leaving group has no resonance stabilization, which makes it difficult for that oxygen to leave in the first place. So now I've drawn in the electron pushing arrows to show the two other resonance structures that this leaving group possesses after it leaves. And you can see that the resonance allows this negative formal charge to be spread out among three different oxygens. The negative charge is spread out between this oxygen, and this oxygen in three different resonance structures. Well, remember, negative charges are more stable when they're more spread out. So the sulfonate is better able to stabilize its negative charge after it's left, which makes it easier for the sulfonate to leave in the first place, making the sulfonate the better leaving group. This oxygen has no potential for resonance stabilization, which means that it's more difficult for this oxygen to leave in the first place, making it the worse leaving group. And in fact, again, an alcohol is considered a bad leaving group. So a sulfonate group is a good leaving group because its negative charge will be resonance stabilized after it leaves. Again, it's not because it's a big group. The size of the entire leaving group as a whole isn't really significant. Only the atomic size of the specific atom that receives electrons affects leaving group ability, and that's a criterion that's not relevant for this example, because in both cases we have the same atom receiving electrons and oxygen. Notice this is another example of the idea that when judging leaving group ability, it's usually best to focus on what the leaving group will look like after it leaves. And again, the point that we just made about leaving groups also applies to nucleophiles and bases. For most of the situations we've discussed in this video, the key factor to focus on was atomic size. But remember that all these trends are based on atomic size, not the size of the entire molecule or group. The trends for nucleophiles and bases are based on the atomic size of the specific atom that donates electrons, not on the size of the entire nucleophilic or basic molecule or ion. And if you have a leaving group that consists of more than one atom, like these, the trends that we talked about in this video were based on atomic size of the specific atom that receives electrons, not on the size of the entire leaving group as a whole. Please pause the video and try this problem. Now let's discuss. We can start by numbering. Now, we don't need to use the table to determine the mechanism because the mechanism was told to us in the problem. So we know this will be an E2 mechanism. We can identify the neutral bromine as our leaving group for the E2 mechanism. So we can identify carbon 1 as our alpha carbon for the E2 mechanism. Now we have to decide which of these molecules will be better for E2. Well, we know that when you carry out E2 on a ring, the beta hydrogen has to be trans to the leaving group. But this molecule definitely has beta hydrogens that are trans to the leaving group. And this molecule also has beta hydrogens that are trans to the leaving group. So that can't be the deciding factor. Sometimes we decide, sometimes we judge E2 by how substituted the beta carbon is. Sometimes we look at the amount of substitution on the beta carbon, but that can't be the factor here because both beta carbons in this picture are secondary and both beta carbons in this picture are secondary. So the substitution of the beta carbon won't be the deciding factor in this problem either. It doesn't help to look at the alpha carbon or the leaving group because both of these pictures have the same type of alpha carbon and the same leaving group. So what's left? What other factor could we consider to figure out a reason why one of these E2s would be faster than the other? These molecules seem very similar. These molecules seem so similar that you might have a hard time thinking of any important differences that would lead E2 to be faster or slower in one than the other. Well, I hope that at this point you would remember that sometimes when you're dealing with cyclohexane, it's important to draw the chair conformation. So that's the key to this problem. We're going to have to draw the chair conformations to decide for which molecule E2 is more favored. And the main clue that you need to draw the chair conformations here is simply that there's no other factors that will help us. We can't see any other way to choose which of these will be faster, so we may as well try drawing the chair pictures and see if that helps us. So if you haven't done so yet, now would be a good time to pause the video and try drawing chair pictures to help you solve the problem. Now let's proceed. Here's an outline of our chair picture for molecule X. Let's number the carbons. The numbers 1, 2, 3, 4, 5, 6 are arranged clockwise in the flat picture. For consistency, we should arrange those numbers clockwise in the chair picture. Now we have to draw the substituents using this rule. The bromine is on a wedge in the flat picture, so the bromine should be drawn up in the chair picture. Up. Carbon 7 is on a dash in the flat picture, so carbon 7 should be drawn down in the chair picture. Down. Now let's draw the other chair flip for molecule X. Let's number this chair flip. Remember that it's best to take the number from the far right of one chair flip and put it on the far right of the other chair flip, and take the number from the far left of one chair flip and put it on the far left of the other chair flip. And because the numbers are arranged clockwise in this chair flip, the numbers should continue to be arranged clockwise in this chair flip. Now we have to draw in the substituents in this chair flip using this rule. The bromine is up in chair flip A, so the bromine should point up in chair flip B. Up in both chair flips. Carbon 7 is down in chair flip A, so carbon 7 should point down in chair flip B. Down in both chair flips. And again, we've illustrated this idea we saw in the previous video. The substituents that were equatorial before the chair flip became axial after the chair flip. Be careful when you're drawing in the substituents to put them in the correct places. For example, I think it might be tempting for many students to try to put the bromine on this carbon. They might seem like they're in similar positions, but notice the bromine doesn't go on this carbon. Also, I think it might be tempting for some people to put carbon 7 on this carbon. This might seem like it's in the same position as here. Don't put carbon 7 in this position. Remember, use your numbers. Use your numbers to make sure that you're drawing the substituents in the correct positions in the chair flip. Now, can you identify which is the more stable and which is the less stable of these chair flips? Here's the answer. Chair flip A is more stable because chair flip A puts the substituents in the equatorial positions. Chair flip B is less stable because chair flip B puts the substituents in the axial positions. We learned in the previous video that it's best when possible to put the substituents in the equatorial positions. They experience less steric hindrance in those positions. I've reflected that with these equilibrium arrows. I've drawn the longer arrow pointing to the left to show that the molecule will spend the greater percentage of its time in chair flip A. And I've drawn the shorter arrow pointing to the right to show that the molecule will spend a smaller percentage of its time in chair flip B. So these arrows reflect the idea that chair flip A is more stable than chair flip B. Now, in which of these chair flips is E2 possible, and in which of these chair flips is E2 impossible? E2, remember, can occur only during the chair flip during which the leaving group is in an axial position. E2 can't occur while the leaving group is in an equatorial position. So E2 can occur only for molecule X only during chair flip B, which puts the leaving group in our axial position. And E2 cannot occur for molecule X during chair flip A, which puts the leaving group in an equatorial position. So, do we conclude that E2 will occur quickly or slowly for molecule X? Well, notice that the molecule will spend most of its time in chair flip A, but during that majority of the time, E2 cannot occur. Molecule X will spend only a minority of its time in chair flip B when E2 can occur. Therefore, E2 will be slow for molecule X. E2 will be slow for molecule X. So we can conclude that E2 will be faster for molecule Y and slower for molecule X. Let's make up some numbers to illustrate that. For illustrative purposes, let's just suppose that the molecule will spend 90% of its time in chair flip A and 10% of its time in chair flip B. Those are just made up numbers, but we know that this number should be bigger than this number because this is the more stable chair flip. So 90% of, so remember that the molecule X will be continually changing back and forth between these two conformations. Sometimes molecule X will look like this, and then sometimes it'll flip and look like this, and then sometimes it'll flip back and look like this. It'll keep flipping back and forth. But we know that but let's say that molecule X will spend about 90% of its time in chair flip A, and only about 10% of its time in chair flip B. Well, during this 90% of the time, E2 will not be able to occur. And only during this 10% of the time will it be possible for E2 to occur. That shows us that E2 will occur pretty slowly. Why is this the more stable chair flip? Because it puts the substituents in equatorial positions. Why can't E2 occur during chair flip A? Because it puts the leaving group in the equatorial position. Why is that bad for E2? Well, when the leaving group is in this equatorial position, it's impossible for it to be anti to the beta hydrogen. Remember that E2 requires that anti-periplanar conformation. E2 requires the leaving group to be anti to the beta hydrogen. That's impossible when the leaving group is in an equatorial position. Notice that we can't use this beta hydrogen. We can't use this beta hydrogen because it's cis to the bromine. They're both pointing up, so it's impossible for them to be anti. Clearly, this bromine can never be anti to this hydrogen because they're both pointing upwards. So the only possible beta hydrogen we could use is this one. But notice that they're clearly not anti to each other. This bromine is pointing up and to the right, and this is pointing down and to the right. This is a down and to the right a bond, and this is up and to the right. They're not pointing 180 degrees from each other. So actually, this bromine and this hydrogen would be gauche to each other, not anti. And that's always going to be true when a leaving group is in an equatorial position. When a leaving group is in an equatorial position, it can't be anti to a beta hydrogen. That's why E2 is impossible when the leaving group is in an equatorial position. On the other hand, clearly when the leaving group is in an axial position, it can be anti to the beta hydrogen. While the leaving group is in this axial position, it can clearly be anti to this beta hydrogen. These are clearly now pointing at 180 degrees from each other. The bromine is pointing straight up, and the beta hydrogen is pointing straight down, anti-conformation. We know now that E2 will be faster for molecule Y than for molecule X. But to fully justify our answer, the professor is going to want us to draw the chair conformation for molecule Y. So let's proceed and draw that chair conformation for molecule Y. We're beginning the chair picture for molecule Y. Number, still numbering clockwise. Put in the substituents. Both substituents are on wedges in the flat picture for molecule Y, so both substituents point up in the chair picture for molecule Y using this rule. Now do the chair flip. Number. The numbers at the far right and the far left in this chair flip match the numbers at the far right and far left in this chair flip. Keep numbering clockwise. Now draw the substituents. Both substituents pointed up in chair flip A, so both substituents should point up in chair flip B using this rule. And again, we illustrate that equatorial and axial flip when you do a chair flip. The axial substituent becomes equatorial, and the equatorial substituent becomes axial when you do a chair flip. Now choose which is the more stable chair flip. The more stable chair flip puts the larger substituent in the equatorial position. Well, the ethyl group is larger than the bromine because the bromine is just one atom, but the ethyl group is 2 carbons and 5 hydrogens. Since the ethyl group is 2 carbons and 5 hydrogens and the bromine is just one atom, the ethyl group is larger, significantly larger than the bromine. So we want to put this large ethyl group in the equatorial position. So I've drawn the longer arrow pointing to the right to show that this rightward chair flip is the more stable chair flip. And I've drawn the shorter arrow pointing to the left to show that chair flip A is the less stable chair flip. The more stable chair flip puts the larger substituent in the equatorial position. Now, for which chair flip can E2 occur, and for which chair flip is E2 impossible? E2 can occur only during the chair flip for which the leaving group is axial. E2 cannot occur during the chair flip for which the leaving group is equatorial. So for molecule Y, E2 can occur only during chair flip B, because that's the chair flip where our leaving group is axial. For molecule Y, E2 cannot occur during chair flip A, because that's the chair flip for which the leaving group is equatorial. Since E2 can occur during the more stable chair flip, E2 will be relatively fast for molecule Y. E2 will be relatively fast for molecule Y because the more stable chair flip is also the chair flip during which E2 can occur. Just to make up some illustrative numbers, suppose that molecule Y spends 80% of its time in this more stable chair flip and only 20% of its time in the less stable chair flip. So molecule Y continually flips back and forth between these two pictures, but it spends a lot more of its time in the chair flip B than chair flip A. Well then, during this 80% of the time, E2 can proceed. And it's only during the 20% of the time that E2 cannot proceed. So E2 would be relatively fast for molecule Y because the molecule is usually in the chair flip during which E2 can occur. I just made up these numbers 20 and 80% for illustrative purposes, but we know that this number must be bigger than this number because this chair flip is more stable than this chair flip because this chair flip puts the larger substituent in the equatorial position, and this chair flip puts the larger substituent in the axial position. Now, as part of your justification for your answer for this type of problem, most professors would like to see you actually draw the mechanism for the faster E2 reaction. So if you haven't done so already, pause the video and draw the mechanism for the E2 reaction for molecule Y. Well, to do that, we have to show the beta hydrogen. Which beta hydrogen are we going to use for E2? Well, remember that in a ring, you have to use a hydrogen that is trans to the leaving group, because otherwise there's no way it could be anti to the leaving group. So we're not going to use this hydrogen, This hydrogen is not anti to the leaving group because it's cis to the leaving group. We're going to have to use this hydrogen. And you can see that clearly this hydrogen really is anti to the leaving group. So for E2 and cyclohexane, you need to use both a leaving group and a beta hydrogen that are in axial positions. That's the only way they can be anti to each other. This problem didn't tell us what base we're using, so we'll just make up a generic base. So here are the electron pushing arrows for the E2 mechanism that will occur for the faster E2 reaction. As I said, professors generally want to see you draw this mechanism for this type of problem as part of your justification for your answer. The professor definitely would want you to clearly show that in this picture the leaving group and the beta hydrogen are both axial, which allows them to be anti to each other. Here again was the problem, and here's our solution. So I've written out a complete set of pictures and a complete written explanation for this problem. I think I've probably written down quite a bit more than you would need to write down during the exam to get full credit. For full credit, you definitely should at least show this chair flip with this mechanism, and you probably should also show a chair flip that shows why the reaction occurs slowly for molecule X. You probably don't need this much written explanation. I've written out a complete written explanation analysis for both molecule X and molecule Y for clarity and completeness. So we finished this problem. Remember, this was the original problem. Notice that the original problem never mentions the chair conformation or chair flips. We had to think to apply that to this problem. What was the clue that we should think about drawing the chair conformations? Well, first of all, we know that this does involve cyclohexane. And whenever we see cyclohexane, it's possible that it will be helpful to draw the chair pictures. On the other hand, we've also seen many E2 problems that involve cyclohexane where it's not necessary to draw the chair pictures, so you do have to use judgment. The main clue that we should draw the chair pictures is that there was no other way to come up with a reason why one of these molecules would react faster than the other. We couldn't see any reason why one of these would react faster than the other without drawing the chair picture. That was a good clue that we needed to draw the chair pictures. Oftentimes, it's important to draw a chair picture for E2 for cyclohexane when there is a very large substituent like a tert butyl group. So this problem was more challenging because we didn't have a tert butyl group, we had an ethyl group. An ethyl group, I guess, is a moderately large substituent. Certainly an ethyl group is not as large as a tert butyl group. So here we didn't have as large a substituent as a tert butyl group. We had a moderately large substituent. This substituent is large enough that the chair flip where the substituent is equatorial will be greatly favored over the chair flip where the substituent is axial. When you see a tert butyl group on cyclohexane, that's a strong clue that you need to draw the chair picture. But you can see that occasionally you need to draw the chair picture even with a substituent that's smaller than a tert butyl group. So we applied these guidelines for cyclohexane. E2 can occur only when the ring is in the chair flip that puts the leaving group in the axial position. So E2 cannot occur in the chair flip that puts the leaving group in the equatorial position. So E2 could occur for chair flip B for molecule X and for chair flip B for molecule Y. E2 could not occur for chair flip A for molecule X or chair flip A for molecule Y. Remember, again, this is because it's only when the leaving group is in the axial position that it can be anti to the beta hydrogen, as you can see in this picture. So you want to ask, so you can see E2 proceeds quickly for a ring where the more stable chair flip puts the leaving group axial. E2 occurred quickly for molecule Y because E2 could occur in the chair flip that was more stable. But E2 is slow for a ring where the less stable chair flip puts the leaving group axial. For molecule X, the leaving group was axial during the less stable chair flip, as we had indicated by these equilibrium arrows. And how do we determine the more and less stable chair flip? The more stable chair flip puts the largest substituent in the equatorial position. So chair flip A was the more stable chair flip for molecule X because it put the large ethyl group in the equatorial position. And chair flip B was the more stable chair flip for molecule Y because it, again, put the ethyl group in the equatorial position. And again, we can indicate the more stable chair flip by drawing unequal equilibrium arrows. Let's try a review quiz. Please pause the video and try this problem. I encourage you to write out your answers for this problem. I hope you tried that. Well, the answers to that problem can be found in the handout. An SN2 mechanism has one main step, during which the nucleophile joins the alpha carbon and simultaneously the leaving group leaves the alpha carbon. An SN1 reaction has two main steps. In the first step, the leaving group leaves the alpha carbon, and in the second step, the nucleophile joins the alpha carbon. But we have seen that SN1 reactions usually also contain a third acid-base step as well. And an E2 mechanism has one step, during which three things happen simultaneously. The base takes the beta hydrogen, a pi bond forms between alpha and beta carbons, and the leaving group leaves the alpha carbon. I hope it was easy for you to remember those details about these mechanisms. You have to be very clear about that because when you take your exams, the professor is going to give you problems with a mixture of mechanisms, and you're going to have to keep switching gears and changing back and forth between different mechanisms. The professor is hoping that students are going to get confused and mix up the mechanisms when they have to shift back and forth between those different mechanisms, and the only way to avoid that is to work repeatedly on memorizing exactly what happens in each of the mechanisms. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen, or by using the link in the video description box. Thank you.